Let's look at the electrostatic energy that is created when we bring together a discrete charge distribution. So before we begin, I just want to remind you of the work done in moving a charge Q from A to B in the presence of an electric field. So imagine we have this field E sub r, and we have a charge Q, and we know that if it's in the field, it will experience a force. And so if we're at the point R, so Q is sitting at the position R, then the force on that Q will be Q times the field at that position. So imagine that you have this point A and B along a path, then the field will produce a force anywhere on that path. Well, we know that if we oppose that force, we could move the charge in the field, and that would be the force that we would have to push with in order to move it. And just remember that this is a conservative field. Okay, so what's the work done? If we're talking about the work that we do, and we'll call that W, so this is by me or you or us to move the charge, it's equal to that force integrated over the path. So we're going to go from A to B. This would be the work done by us or we in order to get that done. And remember, that's equal to Q times the difference of potential between those 2 points. And the way we got this equation was that we let E be the minus the gradient of V, put that here, and then we use the fundamental theorem of gradients to get this side over here. The important thing is all we need to know is the potential at those points. If we solve for this difference of potential, we're talking about a work per unit charge, so therefore we should get a potential. And so we end up with the difference of potential is the work done divided by Q. Now if V is well behaved, then it will go to 0 as R approaches infinity. So for example, all of these charges here, if we go to infinity, the potential created by these charges will go to 0. Let's just let one of those points be infinity, so we'll let A go to infinity. And we know that that is the case then. V infinity is 0, so V of A is 0. All we're left with then is V sub B, and we'll set that equal to V evaluated at R sub B, because that's what we mean by B. And so that'll be W, the work done that we do from pushing the charge from infinity to R sub B divided by Q. So then we want this quantity again, so we just multiply by Q. We end up with the work done is equal to Q times the potential at the point where we stop pushing. Well, that's an important equation, so I put it up here just to remind us. So now we're going to bring in lots of charges. Let's bring in a single charge, we'll call it Q1. And since there's no field to do any work against, and also there's no potential, then we end up with no work. And so in going from infinity to the point P1, which is designated here, which is at the position R1, we get 0. So to bring in Q1, W1 is 0. How about a second charge? Well, now we have a charge Q1, and so to bring in Q2, we have an E field, and so therefore there will be work done. We know that when we're finished, when we're positioned here, the potential at this point due to this charge will be related to the distance between P1 and P2. And remember that was funny R sub 1, 2. Writing that out then, the work done to get to the position P2 or the charge Q2, this will be Q2 times the potential due to Q1 at the position R2. That's equal to K Q2 times Q1 over the distance between Q1 and Q2, which is our funny R. R is our funny R, and if I wanted to, I could put a vector here and a vector here. The distance R1, 2 is equal to the absolute value of R2 minus R1, which we've used many times. One thing to notice is that we can flip R1 and R2 and we get the same number because we're taking the absolute value. Funny R1, 2 is equal to funny R2, 1. So we're not going to worry about the order of these two indices. Okay, so now we bring in Q3, and so the potential that we're dealing with is due to both charges, Q1, Q2, and that's at the position R3 where we put Q3. And so we have Q3 times the two contributions to the potential, and if we go up here, here's our P3, the distances between 3 and 1 are right here. The distances between 3 and 2 are right here. And so if we evaluate the potentials with those two distances put in, this is the work done to get Q3 into position. So let's do one more. Let's bring in a fourth charge. The work that we have to do to bring in the fourth charge will be Q4 times the potential due to all the other charges at position R4. If you remember, then this is the potential due to Q1 at position 4. If we go over here and look at the position of Q4 relative to the three other charges, then we have these funny R's, which I didn't mark, between P1, P3, and P2, and the position of Q4. So what are those? Well, I just represent them as funny R's, 1, 4, 2, 4, 3, 4. So we end up then with the three terms in the potential of the other charges at the point corresponding to where Q4 is. Now we want to do the total work, so we add these up. Remember, this is 0, and then here's W2, here's W3 right here, and here's W4. And realize we're just getting them from these equations that we developed. So here's W4. If we expand this, we can write it as simply just taking away these parentheses, so we end up with this series of terms here. And I'd like to reorder them so that I have the first index 1 here with 2, 3, 4. Then I have the value 2 here, and the ones that survive are 3 and 4. Remember that 2 here is connecting to 1, and 3 is connecting to 1, 4 is connecting to 1. Here we're only interested in the 2, 3, 2, 4. And then finally the third one, the only remaining funny R is 3, 4. We've got Q1, 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 Q2, Q2, and Q3. So repeating that then, if we sum these up, we have then 6 terms in the total work to bring in 4 charges. One thing to notice is that there's no repeated index here. They're all different in these terms. I want to show you quickly, so therefore I've used Mathematica so that I don't have to write all these down. What happens when we take a general term up here and write it like this? So in Mathematica, you'd have a K, that's our K up here, Qi, Qj, Rij, and you have to have a comma here for Mathematica. So that's the term in the work that corresponds to Ij sitting in the position that we have here. Well, we can make a table of all these and forget about flatten. These are the terms if we just take all of them. So we take all possible i's and j's. We don't get what we have above. We get 16 components. So there's all possibilities for these indices, and that includes repeated indices, and it also includes those that just simply switch. So for example, if you look here, we have a 1, 2, here we have a 2, 1, and that continues for all of these. Okay, so add them up. All we do is add these up, and that's what total does. This is equivalent, so forming this is equivalent to 2 sums. You're summing over I and you're summing over j. And so that's what we have here, and this is the same representation of these terms where we have all ij allowed and we just do the summations. So we end up again with 16 terms. We want to point out that you can't interact with your own potential. So Qi cannot interact with its own potential. When we have these terms, this should be W11, and we should have W22 here. So that would be equivalent to having R1 minus R1, which would give you 0. We're going to do that, and in Mathematica that's easy. You basically do an if statement, and if they're equal, you just set it equal to 0. Then you do the same. All of these are the same. So what happens then is wherever you have I equal j, and this is 1, 1, this is 2, 2, this is 3, 3, this is 4, 4, we get a 0. So we add these up and the zeros disappear, and we have everything but repeated indices. This is equivalent to writing it like this. It's a sum over I, it's a sum over j, where we don't allow j to equal I. And so that will get rid of all the wi's. How many terms? Well, we've got rid of 4, so we're left with 12 terms. Now we're going to deal with the fact that it doesn't matter if we reverse the order of I and j. As long as these are different, which we've required, we can set these equal. We can flip half of these indices. So in other words, if you had 1, 2, you could take R2, 1 and make it a 1, 2. So let's do that. To do that, I have chosen that if I is greater than j, then do the flip. Here's the flip right here. Okay, take the terms here, and what we're left with is a somewhat ordered sequence. We have I, 1, 2, but notice that we get the factor of 2. All of these have a factor of 2 because we've done the flip and set it equal to the indices where this is lower than this. So that's what this did here. We took I greater than j and flipped them. And so we end up with the lower order. So you have 2, 3, 2, 4, and then 3, 4. And so all we've done is ended up with these factors of 2 here. There's 6 terms. Recall that the calculated W for the 4 charges had 6 terms. So we're very close to getting the answer by doing this summation. If we go back to this summation here, which counted Rij's twice, if we divide by 2, so we take our answer, divide by 2, and look at this here compared to the calculated one up here, then we have a way of calculating this 4 charge W by using the following. So we divide by 2, and we use the same representation that we had before. We sum over I, we avoid I equal j, and the 2 here is due to the flip, because if we include all of the terms, we have to divide by 2 in order to get the right answer. So this, in fact, is the answer for 4 charges. So repeating that then, if we rewrite that in terms of factoring out q, so we're going to take q sub I and put it right here. There's no change in terms of the value because we're summing over I first, and here's q sub I, then we sum over j, which is right here. But look at this quantity here. Remember that the potential of a point charge is k times the charge, q, divided by a distance to some point that we're interested in. The distance is from wherever we put q. So this right here is the potential of the point charge q sub j at the position of q sub I, r sub I. So let me repeat. We have q sub j here, so this is j, and here we have q sub I, so here's our I. This quantity right here is the potential at q sub I due to this charge here. So that's what this says right here. That we represent by somewhat complicated notation, but this is Vj at r sub j. So that's where the q is. I really should put Qj at r sub j at the position r sub I. That's the potential. So if we rewrite this, then we would have our q sub I here, and all I've done is put in the V notation for this quantity right here. And so this would be q sub j at r sub j. So this is the sum, and we'll use the notation that we had before. So we're just looking at this second summation right here. We're summing over all of the q's, so this would be the total potential due to all of the other charge at the position of q sub I. The total work done will be 1/2 times q sub I times that total potential due to all the other charge. So this is a relation which gives us the work to assemble these charges from infinity. 0, and then we have to bring this one in, this one, and this one, and they're all dependent upon the potential where we end. So that's why we end up taking a q sub I times the potential due to all the other charges at r sub I. Just to remind you, remember when we moved a charge from infinity to r sub b, we ended up with this quantity here. So one term of this expression here, this is just for one charge, is equal to this. Then we sum over I. We can generalize this. I built this up to 4. We could keep going, but they would all look the same. So if we go to n charges, then all we have to do is change the index up here to n, and we get the correct answer. So this is the work done to assemble n charges at the positions r sub I equals 1 to n. So next time we'll look at a continuous charge distribution and look at the same concepts of creating a continuous charge distribution and relate it to electric field.